Yeah, online participant, can you hear us?
Yes, sir.
Okay, thank you. Hello? Yeah, am I audible? Online participants? Good. Okay. So good morning and welcome back. So
Welcome back.
so hello. Yeah. So plan is that morning we'll just quickly go through the compressible flow equations and then followed by the hands-on session on the compressible flow equation. I think yesterday you have kind of done the incompressible flow. Now there is one basic difference between the compressible and incompressible. So when we talked about the incompressible flow equation, we kind of emphasized on splitting the pressure and velocity and then solving that to the mass corrections equations, which is the pressure Poisson equation. We do the corrections and then move on iteratively. So those are primarily called pressure based algorithm or pressure based solver. Now, similar approach you can. So now what happens in the compressible system? Your density is no more constant, or I would say density variation is quite high compared to incompressible case. Incompressible case, my density variation was not that much, which was negligible. That's what most of the time you tend to ignore the density and solve the system. But obviously, one thing there could be exception like when there are variable density flows, even a low Mach number variable density flows like your reacting system is one of the prime example where density is varying. So you have to take that into consideration through equation of state and things like that. Now, coming back to that splitting approach that we have done, since the compressible case, my density is no more negligible. I would put it that way. So density variation is quite high, rather substantial. So I need to take that into account. So what one can do, you can still do that kind of decoupling. But obviously, the equation, if you remember the incompressible equation that you had, divergence of u is 0. So now it's not going to be like that. So you'll have a density sitting there. And when you decouple that, all your velocity components will have a rho u, rho v, rho w like that. So I can still do in that fashion, but that is not something is very commonly done or not something is very advisable to do, because in that way the convergence of the mass correction equation becomes little tedious or problematic. So that's what it is kind of avoided. So what it does in compressible system, we do in a solve the system in more like a coupled fashion. So instead of splitting pressure and velocity, you try to keep everything together. So this probably the equation, if you try to look at it, so the equation same. I mean, whatever we had here, the variables are all having an extra addition to that, which is density along with that. So, and rest of this is your convection term, the flux, and along with my pressure gradient, and this is my diffusion, typical diffusion term, and if you have a source term. So if you see here the variable that you are solving, it's not explicitly u, v, p, something like that. It has the rho sitting in front of it. So in the compressible system, the most suitable method could be solve everything in a coupled fashion. So you keep all these together. So you don't decouple the pressure gradient from the system. Rather, you have it together and you try to solve it. So that means I have to kind of keeping this uh, flux, which is there convection. Viscous flux, I am not worried because it was there earlier as well. So issue comes in two sense. One is that density sitting with all the primitive variable. Second is that I can, my pressure gradient is also coupled to the nonlinear convection term where I cannot, I mean, it's not recommended to decouple. So this school of or the solvers, whatever you get in compressible system, these are called density based solver. Okay. Whether in incompressible system, what we had when we try to decouple, it was a pressure based solver where my correction term is obtained through the pressure Poisson equations, which is satisfying my mass conservation equation. Here we still do have the continuity equations and all these things, but here I'm not going to decouple. I'll solve the whole system in a coupled fashion, and these are called the density based system. Now the obvious question which may arise is that if I have a density based solver which is having rho, and I mean if I look at the primitive variable setting rho and all these things, cannot I use it for my incompressible system where density variation is negligible? So eventually that's going to give me the same sort of solution. So ideally what should happen? Can I use it? I mean, if I have a system like this where everything is coupled, and in case of incompressible system, my density variation is negligible. So still this rho might be not varying that much. So rho could be kind of treated as a constant. Can this system be used for my incompressible flow equation? What do you think? Yes, no? Yes. So answer to that is yes, we can, but we don't. That's a something different. Theoretically, whether we can or not, yes, there is no harm in it. There is nothing I am violating. Everything is perfectly fine. But in practice, we don't. Why? What happens is that when you try to use this compressible based solver purely in compressible based system, the algorithm that you use here, it's slightly different, which is not easy to converge when you go to that limit of incompressibility. So that's the problem. It's more like an issue related to numerics. So that is why it is recommended if you have a strictly incompressible flow system, try to use incompressible based solver, which is pressure based solver. If you have a strictly compressible based system, try to use the compressible based solver, which is density based solver. This guy can be used, but not recommended because of the issues related to numerics. Okay. So here what we do, we would adopt a different algorithm. Now, I mean, obviously this we just to refreshing this, you can have all different kind of grids that we have already talked about: structured, unstructured, block structure, this kind of body fitted block structure or similar technique kind of grid. So different kind of grids you can adopt. So now the solver part, which we have not explicitly talked about yesterday, is that now I can have a two different kind of solver. One could be structured solver, one could be unstructured solver. Now, what does that mean when I say that structured solver and unstructured solver? The, hmm, check if there is any comment or not. So, what is the difference of between structured solver and unstructured solver? So, what do you think? Is that the how what kind of grid I am going to use? Based on that, I am going to define the solver, or it is something else? What is the thinking? It has nothing to do with my input grid structure. Structured solver is something where my whole algorithm is treated in more like an convenient fashion. Continuously, my directions would be I, J, K, whatever it is. They are in a defined in a structured kind of fashion. Okay, more or less like an you can think about, which is more orderly fashion like this. Okay. So I have everything going systematically like this. So that means when I read it's more like an you can think about in a simplistic fashion is the data structure, how I have defined the data structure. Data structure is more like an continuously defined data structure where I have all the system or all these things are defined in more orderly fashion. So the whole algorithm or the solver is going to read the data structure in that fashion. It's going to treat the data structure in that fashion. Now I can define my geometry in terms of grid in that fashion. The solver would read and do his job. Unstruct. So that means what it does in in other way is that, I mean, if I have a structured solver like this, so all these fluxes are defined in a systematic or orderly fashion. So if I can define my geometry in this kind of data structure, then it could be red. Unstructured solver is that the algorithm is such that, say, same this kind of technique I can do like, let's say I'll split like this. Now here I can maintain a sequence 1, 2, 3, 4 like that. But here if I have a system like this, I cannot maintain a sequence like that. What I have to maintain here is that the connectivity matrix. That means if these are my individual cell element, then what is the neighboring cell? What is the vertex which is connected to the neighboring cell? What is the face which is connected? So it's more like an connectivity matrix that I have to take it into account. Now, if you think about in terms of finite volume, here the normal fluxes are calculated, which is always normal to the or perpendicular to my surface or the face, cell face. Here, if I have an element like this, the normal probably would be, if I talk about this element particularly, red. Here the normal would be probably, if I talk about this, the normal would be probably in this direction. In this case, it was more orderly. Normal is like this, perpendicular to mine. So in finite volume, what I need, it's a conservative scheme. So I do all the governing equation conserved over the cell surface, and there my surface normals are required to be calculated to conserve my fluxes across the surface. Here the normal is in different direction. It is perpendicular but different direction. So this flux conservation calculation is entirely different compared to this cell compared to this. So my algorithm, which can take care of this kind of arbitrary normals and things like that, that is what you think about. It's an unstructured solver. It has nothing to do the kind of grid I'm giving as the input. So the normal calculations. So obviously you can imagine the data structure definitions are going to be different. So it would be much more, I would say, the tedious job, because you have to keep track of a lot of things. This cell connected with this cell connected with this cell connected with this cell. So which is the vertex which is connected, which are the neighboring cells are there. So all these normal calculations, those goes, and those are trigonometric properties, nothing like that. But I need to keep track of those information. So my solver, which is capable of handling this kind of arbitrary structure, that's called the unstructured solver. So it has, again, I am reiterating, it has nothing to do the grid I am giving as an input. So if I have a unstructured solver, which is unstructured solver are robust in nature because it can capable of handling different kind of geometries. That's allow me the flexibility. When I have an unstructured solver, it can take any sort of now grid element that we have talked about. So for example, if I go back, any grid you look at it, the unstructured solver can handle. Even the one which I have shown yesterday, the prism element, this element, tetra element, hex element, all the different kind of elements it can do. But if I have a solver, which underlying algorithm is structured solver, it cannot handle all sort of different element. It can probably would be able to handle this, probably this, not this. So other way around, I can say here, like my compressible, incompressible, structured algorithm is a special subset of this unstructured algorithm. If these things become a perpendicular to each other, then it becomes a structured algorithm. So this is much more robust in that way. So one may immediately think about, if I have a structured solver, cannot I handle a curvilinear geometry like this? If I have a geometry like that, cylinder, cannot I handle it in a structured solver? Or is it an unstructured solver that I have to do? I can do both. Okay, but to handle this case, I might need to do one of the other of the techniques. Either I have to generate grid like this, or obviously I'll generate grid like this, and then in the solution algorithm, the algorithm has to take into account that thing, because my solution algorithm probably works or understand typically this fashion. This kind of ordered fashion it understands. Okay, but now if I have a grid like this is not, it is a structured grid, but not in this fashion, ordered in this fashion. So I have to do some kind of a transformation. Okay, these are called Jacobian transformation, which internally you have to do. You read the grid, do the Jacobian transformation, then your solver would be capable of handling. But obviously in doing that transformation, your accuracy, error, precision, these are becomes a question. So unstructured solver is much more robust in handling different kind of geometries, but at the same time, it's a bit complicated for programming and implementation point of view. This, we have been kind of grown up from childhood, looking at visualizing these things so easily. So it is easy to comprehend, easy to implement, but it has its own restriction. At times or at cases, this is probably much powerful than this, but this is much more robust. So it's always a trade-off to some extent. And the commercial packages that you primarily use in CFD like ANSYS, COMSOL, these are all unstructured based solver, including your OpenFOAM. But that doesn't tell me whether I should not giving a structured grid or not. That has nothing to do with that. Solver algorithm is based on the different logic. The calculation of normal is different. Tagging of the data structure is different. So it is much more robust. So that's why these solvers allows you to handle any kind of complicated geometry. That's the robustness comes from there, the way I have devised my algorithm. Okay, so now coming back to the compressible part equation, because this was bit important to understand how these two different things work. So the compressible part equation, I have the whole system written in three set of equations. These are my primitive variables, which is having rho u, rho v. These are my convective component. These are viscous component. This is source term. So what you do that, and if you look at a particular element like that, which will having 6 faces. So this is a 3-dimensional element, and I am having my normals in all directions. So first step, you try to write this guy in this fashion. So you try to linearize it. Omega del W by del T, and del W by del T, then you equate in this fashion. And from there, you go to step 4. So you do a little bit of discretization. So here you see this how I'm discretizing. So this IJK, I'm trying to tag it, the cells which are there. And then you write the simple discretized equation for that particular cell across all the surface. Okay, this is the equation you finally get. And the right hand side, you term it as a residual, what you are going to calculate and try to look at that. Now, this is a busy slide, but don't get scared of it. If you have a 2-dimensional element, then that omega that you have inverted omega or whatever you call it that you got, this boils down to the area of that element. If it is in 3-dimensional, that becomes the volume. And these are the calculation for that, what OpenFOAM does. Okay, essentially, you see that it is taking care of all the coordinates and doing that calculations of the. So as soon as you feed the grid, the system understands whether you have put it a 2-dimensional grid or 3-dimensional grid. It will try to get the coordinates, calculate the area of the volume, because that is what is going to be directly in my equation system. So it's just doing the calculation of the area and the volume, nothing else. Okay. Now, here we are not going to the staggered formulation or these things. Since everything is solved in a coupled fashion, we are sticking to the collocated formulation. That means I have all the flow variables, including my scalar variables, they are defined inside the cell center. Okay. And then I am calculating all my fluxes. So once you do that, then you have to estimate the fluxes across the surface, and that in a typical fashion you take this cell center and take their values and do means. So this means could be calculated in multiple ways. Some can take a simple arithmetic mean, some can take some geometric mean. So there are different means one can add up. It will change your order of accuracy of that calculation. Okay. So this is doing the calculation of those average and the average fluxes across the surface. So idea here is that I have a cell, I have all these variables available at the cell center, and I'm trying to calculate the average fluxes, and at the same time I'll get my source time approximation also. Now okay, now I'll come to this two-dimensional structure here. If you see, these cells are marked as IJ. This is cell upstream of it. This is another downstream of it. This is another downstream of it. So these are my cell coordinates. And using that, what you calculate is that IJ minus half, which is means IJ is here. IJ plus half would be here. And J plus half would be here. J plus 1 is here. J minus half is here. J minus 1 is here. So you try to calculate the average fluxes for these two-dimensional cells, and similar way for the three-dimensional cells, where you take these different surface points and do kind of an averaging. The point here, what you are trying to do is that if I have a cell like this, my fluxes are calculated at the surface. So if it is Ij, this would be sitting at Ij plus half. Or okay, so if this is Ij, this is at the Ij plus half, this is I plus half j, this is I minus half j. So I need to calculate these fluxes in all these four phases. So that is what the done with some kind of an weighted averaging. Now one can say, why do I need to do that? I have all the information, don't need to do that. That is done typically to minimize the error and also to spread over the information over surrounding some of the cells, so that you don't want to have a numerical stiffness in your matrix. It's just a numerical trick, I would say, to avoid your numerical instability. Okay, nothing else. So now if you look at this control volume, I have these average fluxes which are calculated at these phases, and the variables are also average. So these are all done, and I can have cell like this. But as I said, visualizing a typical structured cell and unstructured cell, there would be different. That's what we not showing that, but the calculations is done in same fashion. But you calculate the normal, you calculate the distance among the cells, and then you try to do that. Now, what is here is important is that in the major challenge that you face in the compressible flow is calculating the fluxes for convection term. Diffusion term is not the problem. Diffusion term is always a nice guy. You typically do central differences and things like that, but the challenge you get is the convection term. And convection term includes your nonlinear term plus the pressure gradient term, which is the combinedly convection term. So if you do central differencing in, you can do splitting algorithm. So these are different kind of things that one can do, and OpenFOAM has all the possibilities that one can do. But it is good idea to do some kind of a splitting. So the fundamental goes here is that if I have a cell like this is again to make you understand, we are going back to the one-dimensional just a stencil. So you see this is I plus 1, I, j, In between every cell I and I plus 1, I have the surface interface, and I and I minus 1, I have the interface. My variables are stored at the cell center, I plus 1, I plus 2, or I minus 1, I minus 2. But at the interface, I will be calculating the fluxes. And also, every interface, if I look at it, the fluxes are going in two different directions. One, we call it a left direction surface. Another is the right direction surface. Okay. What does that mean? I have a cell. I have one interface this side, one interface this side. But even in a particular interface, like let's say this is I plus half. If I look at this interface, I'm saying there would be a left side and there is a right side. Why is it so? Because this is a compressible system. So you have sound speed which is associated with that, which makes the system to behave in a hyperbolic manner. And the basic nature of the hyperbolic wave equation system is that your information propagates. If I have a point here or the solution point, how would my information propagate? It will propagate in two different directions based on my local speed and the sound speed. The characteristics would be u plus c, u minus c. That's the characteristics of hyperbolic PDEs. Okay, this is what it is here, because it's a compressible system I have, which is sound speed is there. Because of that sound speed, one end I have the sound speed, I have the local flow speed. So it makes two different characteristics which would the information can propagate. That is why every interface I have to have a left side of it, right side of it, assuming the information is propagating in two different directions. Sometimes it may contribute, sometimes it may not contribute, but I need to take that into account. Otherwise, what will happen? Let's say if I have a sharp gradient there in terms of a shock. Shock is a just stand up sharp gradient. I would not be able to capture that. Yeah. If I don't have a shock or any sharp gradient, probably, yeah, supersonic flows, it always contributes. But if I don't have a sharp gradient, even the supersonic flow, the flow could be naive. I still have a high speed flow, but not necessarily every time shock is interacting, there is a stand-up shock or reflected shock. So those location, it will have a much more sharp peak. There, the information would go in two directions very strongly. It is like contribution in a sense, there would be strong contribution or small contribution, but contribution would be there. Okay, because my local sound speed is also varying with the flow condition. C is also varying with my local flow condition because my density is varying, temperature is varying, which is typically gamma T square root of that. So that is also varying. So that is going to be, it's the characteristics of the sound speed which is going to kind of dictate that characteristics of the information. Okay. So now here, I'll try to calculate both the information in two sides of it. So that means I have a cell. I'm so far we are only talking about cell interface. You have the fluxes, but now one step further, even this interface, I want to say there could be information. Left side of this interface is different than right side. That's what it is. That is what every interface in compressible system, you need to have two properties or characteristics that you need to calculate. Is the left side information of that or right side information? And now how you evaluate that, that can change the compressible algorithm different. One, which are things which are listed here. I can do central differences, I can do splitting, I can do multiple of. So this calculation of left propagating characteristics and right propagating characteristics makes my algorithm again different inside my compressible system. So central differencing, it's just simple. You do the take the left cell and right cell and you do the calculations. Okay. Now, when you come to the cell vector scheme, then you can also use some kind of a upwinding. And upwinding would take into account, see, this is R means the right, L means the left. So upwinding does the calculation in that fashion. So you take the contribution from both the cells sitting in the ahead of it and cells behind of it and try to estimate that left and right phase information. But I can use different techniques. So here's, anyway, that's a cell structure. So this is my central scheme, how I use the simple cell structure like that. I have IJK. These are my cell centers, which I have shown like here, 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 here. And if I have a three-dimensional structure, so central does in a very simple fashion. When I have to calculate the properties here, I'll take the contribution from the neighboring cells straight away. I won't do too much of it. So it's very, to some extent, you can think about doing the mean. The mean works fine for most of the cases in incompressible situation, but here it can create trouble for you. So you need some sort of, and because propagations of, so these calculations, I'm not getting into the mathematics details because this they are in the system, but if you understand the uh, what I am going to show here, and skip this. Okay, so central does the things in a simple way. I can do the splitting also. This is one of the things which is called the vector flux vector splitting. That means the total convective flux that you have, which includes my nonlinear term of the velocity and the pressure, I would split it in two components, plus and minus, and then that also goes through the, I mean, just for reference, you think these are all taking care of my local Mach number in the left side, right side. So if you see this M and all these things, these are Mach numbers. So these are nothing else apart from doing floating point calculations, but taking care of the properties. Okay. Now, if you ask me how do you obtain these and all these things, we can do the mathematics and you can obtain this. But if you get into that, that's not going to work out at this moment. Okay. So what you take the message from here, I have this convective term. I'm splitting in two components, plus and minus. That is what is called the flux vector splitting. And then this finally, end of the day, I need to get these two components evaluated based on the local Mach number. And these are all sitting there in the Mach number calculation. Now, even these calculations can be of multiple type. Okay. And it can be a different algorithm like this one here. Advection upstream splitting method called AUSM, which is very common. So again, if you see the FC term, it has the nonlinear term and the pressure gradient term. You try to split it in the left and right or plus or minus splits. And the splitting calculations are different. Okay. So that makes it's a different algorithm. So you have bunch of this kind of splitting algorithm which is available in your open. So just to list that out, you can have central scheme, you have the splitting algorithm, you have the second order upwind scheme, switcher. All these are, if I'm not wrong, I mean pretty much these are all available in your open. I mean, but the idea based on which these things are done, simply I have, I mean the compressible system, the challenge is that how do I tackle my convection term, which is mostly nonlinear term. And how do I do that discretization? It's a numerics. It gives me a different flavor to that. Now the hands-on that you would be doing is based on the row central form. So which is purely a density based solver. That means everything you are solving in a coupled fashion. You will not be decouple anything. That's what the some of the properties, like it's a density based solver. It's in collocated system. Central upwinding scheme is a blending of that. You can apply to any maze, high speed flows and all these things. Some of the interpolation methods that one can do You can do piecewise parabolic methods. You can do you can do, I think, these are not available in your open form. These are advanced technique, how you interpolate these things. Even when you talk about this splitting of this information at the interface, how I'm doing that over the stencil, these are the different algorithm. Algorithm is, in a sense, you think about some kind of an floating point calculation, but more involved. How they differ from each other? Someone claims that I can capture shock more precisely. So shock has a very good, I mean, it's a very, very thin layer. So that thin layer, which is way less than your cell size, you cannot make your cell size of that structure, which is, I mean, the size could be, the shock size is not even sometimes millimeter. So you cannot make your cell in that fashion. So capturing the shock is a challenge, and the shock can exist right here, not necessarily here, right here, right here, right there. So that would allow me this different algorithm to handle those shocks, how accurately I can resolve that thin structure. Okay. Okay. So they are not available in your open form. I mean, if you do advanced algorithm, if you do your development, you can bring in those. Okay. So the central scheme that which is readily available in row central form is the Kruganov-Tadmor based scheme or Kruganov-Noel-Petrova KNP scheme. Both of them are central appoint kind of system, which is readily available. I would say they are quite robust, fairly stable, even a wide range of high speed flows, not only supersonic, even at the hypersonic range. Any other splitting algorithm, the sophisticated one we're talking about, I can tell you from our experience, some of the other fails in some different regime. So do you want a robust one which will work for you, or you want a something which works for a particular smaller segments? Even in supersonic flow, if I go to 1 to 2 Mach number or 2.5, 2.5 to 5, 5 and above, each of these different splitting algorithm behave in a different way. Their behavior is totally weird. So those comes with some experience. You do some. Okay, these are the combined equation that you have been solving: continuity, momentum equation, everything coupled. I'm not decoupling anything, and the energy equation. Without energy equation, you cannot solve any compressible flow equation. This is a total energy. That means it will include your kinetic energy component and enthalpy. That means enthalpy plus kinetic energy is going to be your E. From here only you evaluate your temperature as a subset. You don't solve temperature explicitly. Okay, so these terms you can. So here, as I said, the cell could be looking like that, and you see the normal calculations. Like if you look at this cell face, here is the normal, but the neighboring cells connectivity is different, so they are already off. So this is what the advantage of unstructured algorithm, which takes into account this kind of calculation. So this involves lot more mathematical expression to be calculated. But what you need to do, you need to calculate the vector which is connecting between two cells. You need to calculate the normal vector, surface vector SF. You need to calculate the radius vectors from one surface to that cell, this surface to that cell. So 3, 4, just the properties that you need to calculate and store it. So the way this algorithm works, you start, then you calculate your fluxes. There you can use different interpolations, and then use your this KNP or KT type of algorithm. Finally, you stop it. That's how the globally the. If you look at the slightly discretized form of the equations, here is the, essentially this is my term which is creating problem. That's the divergence term, del dot del psi term, u psi term. Psi could be my u again, psi could be my t again, psi could be my u energy. So if you use this using the divergence system, so finally you get this summation across the surface. So volume integral comes down to the surface integral, and this phi f which is across the surface I need to evaluate. Okay. So Yes, this is the convective term. So here the in KT method, the alpha value would be, so the lambda f is calculated taking care of, you see, this local sound speed, surface normal. So these are the characteristics which I was talking about, C plus this and phi C minus this. And then if you use KT, alpha is taken as a half. If you do KNP, it does in a different way. And then you calculate for this parameter omega f, which will just require in the next slide. And then finally, I evaluate my end of the day. I need to evaluate my surface fluxes, which is represented like alpha SF psi f. So now alpha is like this. What is the method I'm using, KT or KNP? SF I have calculated as soon as I read the grid. Psi f is the flow variable that I need to calculate at the interface. That time I can use my neighboring cell information. I can have TBD kind of interpolation. I can do window interpolation. So how you do that? This psi f will be calculated. So this is how you estimated that. And then the Laplacian term is more straightforward. So you don't have to do too much of it. So straight away. But since the solver is unstructured, you take care of the non-orthogonal corrections, because if you have a structure like this, you have a orthogonal system, but this is non-orthogonal. So that corrections you need to take in. Any unstructured solver, the orthogonal system means it boils down to a structured solver. So the non-orthogonal corrections you take into account here. And this is how, so you start the, first you solve the density or continuity equation, use that, go for a calculation of energy, combined with the equation of state, you do the viscous part and move on. If you look at the portion of the code, these are the some of the variable that you would be defining. See, any pause or neg means it's at this interface positive and negative, which is my right and left. So anything with pause and nose. So that means I am calculating every variable. You see that rho pause, rho plus, rho minus, rho or rho r, rho l. Rho u means the syntax is easily understand. Rho u means rho into u. R psi is that 1 by r. That is also positive. E is the internal energy, positive, negative. P positive, negative. So each of these positive, negative you calculate, and sometimes if you multiply rho u, that you do, rho energy you do. And here the surface flushes, positive, negative also you need to calculate. Even the surface normal, you take the positive and negative. So this is the complication comes because of your unstructured algorithm. Had it been a structured algorithm, I have not that much of problem. Then you calculate the sound speed also positive, negative. Then you defined if it is Tadmor, then that alpha that I have showed you 0.5 or not. So all this goes into the calculation, and you can from the control input you can set whether you want trad mode or KNP. Okay, and finally you calculate this phi u, which is rho into pressure and all this, and solve the energy equations. Okay, so these are straight away what you see in the equation, they have been kind of converted back. So first you solve the density equation, ddt of rho into rho phi. As soon as you solve that, you solve the momentum equation, predict a step and the update it. If it is inviscid, that means I don't have to solve the viscous term. Otherwise, I have to solve the viscous term. You solve the energy equations. So mu effective takes care of your turbulence and the laminar and all this. You correct the energy, update with the boundary conditions. If you have turbulence, I mean non-viscous system, you calculate the Laplacian term and move on. So you combined equation. So here I'm not doing any splitting or anything of the pressure or velocity. I solve continuity, do momentum. If it is viscous or non-viscous, I solve the energy. If viscous, I solve the viscous terms, including turbulence, non-turbulence, update the system. And then you update through the equation of state, P equals to rho T. So that everywhere in the domain, you update the system and continue with your solution algorithm. Okay, any questions? Quick questions or anything? So, okay, these are some calculations. I mean, just to give you that what kind of calculations one can do, but this is doing at the injector efficiency of a high speed flows. Again, this was looking at the acoustics. This is a hypersonic intake. Uh, Thing is that, so the problem that you will be solving, one is the shock tube problem. So you have a high pressure and low pressure, and in between there is a diaphragm. One that actually breaks how the shock propagates. That is one of the problem that you will be solving. And you will be solving another one is this kind of a flow across the step. Okay. And you can get to see this kind of structure and things like that, which is a Mach 3 flow. So leave it, leave it. I think if time permits, probably this one also is there in a plan, right, Anurag? Yeah. So this is getting into a corner and the wedge, but depends how you move fast, because the thing what it is that compressible calculations, even at the large scale calculations, is much more time consuming. Okay. In a sense, order of months. I mean, overnight, you don't expect, obviously, shock tube you can do in 2 minutes, but shock tube is not something which serve your purpose. But one thing I would like to just comment upon is that, see, this is a good package, OpenFOAM, obviously freely available, readily available. It can definitely serve your purpose, but you have to really work on it. Okay. It's a freely available. That means today I develop something, I just put it in the public repository. It not necessary it is well tested for you. Today I got a new idea of algorithm, I just implement. Okay, it compiles, I just post it in the library, which doesn't mean this is going to work for you. It is tested. Anything you take, you have to do rigorous testing. Then you can modify as per your need. You can do, and you can carry on your development. Development is easier here, but not necessarily. See, a lot of people using OpenFOAM across the world. Everybody is doing some kind of a development. Not necessarily everything is freely available. I mean, just to comment the kind of examples I just showed you, because we have been doing a lot of things. These are not readily even available. Okay, like row central form, we don't readily available solver we don't use. We have a modified row central form solver, which is not readily available. So you have to actually, essentially, you have to develop your own program as per your need. But this is a good platform. It's just like you have nothing or you have quite a bit of thing. So it's just like I have give you the land and ask you to build a Taj Mahal, or I will give you at least the basement of the Taj Mahal and say that ask, okay, build the Taj Mahal over it. It's the choice is yours. What do you want to do? Okay. Thank you. Hello. Hello. Yeah. I think we'll break for 15 minutes. By 10:15, we should be back. No. So by 10:15, we should be back for the hands-on. Okay.
I hope everybody is here. Okay, so today we are going to look into the compressible based solver, which is row central foam. So if I hope everybody is now able to log in into their respective accounts and they can access their folders as well. So so I am in my folder. You please navigate to your particular folders and we shall look on to OpenFOAM day 2. So inside this, we have a compressible folder, right? And I have already customized the cases that we are going to look today. First one is the forward step, uh, which is typically something like this. So a shock tube is there. I'm sorry, we are first going to look at the shock tube. A shock tube is there in which there is a difference of the states on the left hand side, which is the red color, and on the right hand side, it is the blue color. And in between at x equal to 0, a diaphragm is sitting over here. At x equal to -5 is the extreme end of the domain, and another extreme of the domain is x equal to 5. And this is the one-dimensional case that we are going to solve today. So the discretization is just carried out in the x direction, and y and z directions are not solved. Uh, and typically the properties across the diaphragm on the left hand side is tabulated over here, and on the right hand side it is tabulated over here, right? You go to shock tube case. So these are the contents. Uh, First, I will explain the contents of original files. This we need in order to conserve the variables or to make a original copy of the variables. So if you open pressure, it is saying that this. Okay. So typically, the computational domain would look like something like this. And we are just discretizing the domain in the x direction only, right? This is my x direction. This is my y direction. This is my z direction. So this all faces, the hidden faces behind it, right? This all faces are termed as sites in my simulation. These faces are all sites. So it is basically zero gradient across all. And this one, this is the front face. We are not going to solve in this direction. So it is empty, right? So typically nothing should cross across the sides of the faces. So I'm just putting zero gradient. And for u velocity, again, I'm not interested in transforming information across those sides. So again, I'm putting zero gradient. The only thing is we want to initialize what we want to do is we want to initialize the domain something like this with different states that we have not taken care into account. So inside the constant folder, inside the system folder, if you look, there is one important file that needs to be given for setting the initial conditions of the solution or of the problem. So what it is doing is it is first identifying the domain. The default values are, if I convert that set fields into the code, if x is between -5 to 0, right? Then use the left state, or else use the right state. Or let me tell you, use the red one or use the blue one, right? So x is varying between -5 to 0. So in my initial condition, x is between -5 to 0. I want to initialize the solution with the red state. So set fields, I have given explicitly red state as pressure something, some value which is basically 10 to the power 5, and all rho and velocity and all those things are given, right? And on the right side, it is being identified through blue. You don't need to do anything. Blue stated else statement, and that is what default it is doing. Here it is little difficult to visualize. Default values, it is first executing this else statement. It is completely filling the domain with blue color. And then after it is identifying if x is between -5 to 0, it is picking up this particular region and filling up with the left state. So this is what set fields is all about. You can give any, if you want to do, let's say 3 different states. This is also possible. Just need to identify the regions -5 to, let's say, some x1, x2, x1 to x2, you can set the conditions, and x2 so on, you can also set the conditions. This is a typically important function that you need to solve for initial value problem. Sorry. Okay. So again, like previously, that is a cuboidal domain. This is how things look like. Right. So my domain is something like this again. Like in lid-driven cavity, we had a cuboid, nice cube domain. This is cuboid domain, right? So back plane is situated at z equal to -1. From this coordinate, I can say these 4 coordinates. And on the front side, z is equal to +1. And rest -5, -1. My x would be situated somewhere over here. So my x is at the center of this domain, exactly at the geometric center. So it is -5, -1. Then it goes to +5 over here. It is 5, -1 on this line only. Then it goes to top, 5, 1. Right. And on the other side, it is -5, 1. So this completes the complete set of the coordinates on the back side of the domain. And on the front side, again, this would be 0, 0th point, first point, second point, and third point. Similarly, similar nomenclature has been followed over here: 4th, 5th, 6th, and 7th. Right. And if you again go to the blocks, this is a simple whole block that we are going to use, and that has been discretized with 100 of the control volumes. Right. And we don't want the discretization in y and z direction. This is just a 1D problem. Again, we don't need the edges. So typically, I was wrong earlier. This is the sides. This is typically the side, the extreme X position and the extreme left position and right position. These are typically the sides. And rest of the faces, rest 4 faces would be empty. So this is typically exactly what we have identified. 1, 2, 6, 5 would be comprising of this particular face, and other would be 0, 4, 7, 3. You can look into that. And rest of the faces has been declared here as empty. So this is block mesh. Inside. Okay, okay. Inside box to cell, it is 0, -1, -1, somewhere over here. Zero is at the center. Just go, if you want to identify this box, go at one of the extreme, 0, -1 and -1. And other extreme would be come to the front plane and choose the extreme point over here, 5, 1, 1. So it will identify a diagonal and then select that particular box. No, it is not associated. You just need to identify the diagonal. Yeah. So typically we have covered block mesh, we have covered set fields, and this is typical entry that is needed in the schemes file. So compressible flow solutions are very sensitive to schemes. So today in the lecture, you have seen that there is KNP flux splitting and KT flux splitting. So two schemes are available inside row central form. You can choose either of them. So if you use just write Trubnov over here, it will go into KNP flux splitting. Whole kind of mathematics is available inside the paper that I have already shared with you inside that case file, right? And if you write Tadbot, right, it will give to this KT flux splitting. In literature, it has been said KNP is much more better than KT flux splitting. This is very dissipative. If you're capturing a shock, the shock should look like this from one state P1 to another state P2. Very sharp, just vertical inside this cell only. But in reality, your solution will look something like this, very wide. So this width of the shock is what we are interested in. Most of the schemes is able to capture the width very thinner. Then we can say that it is very good scheme. The more the less the width, the good is the scheme. So KT gives very wide kind of very thick shock structures, which is not okay with us. So again, if you look back, we have the temporal discretization as Euler, gradient scheme as Gauss linear, again central differencing, divergence scheme as again central differencing, and this is the important property, which is reconstruction of primitive variables onto phase center. So just today in the morning, you saw there are two control volumes, let's say in one direction, right? And there are again another cells. I'm interested on this phase. I want to calculate flux on this phase. This is the interface. Let's say F. What I'm doing is this is my plus state, this is my minus state. Or let's say this is L and this is R. So what I'm doing is I want to since my data is, I'm writing a cell-centered scheme, all the data, density, velocity, pressure, temperature is available at this cell phases only. I want those variables to be incorporated over here. I want this information to be over on this phase. And since this is a flux splitting method, I want information from both of the states. So what I will do is if depending on the accuracy of the scheme, I may use various number of cells, do some kind of mathematics, and bring those information over here from the left-hand side of the spaces only. The right-hand side will not be used. And from right-hand side information, I will use all the information that is on the neighbor of this cells only to increase the accuracy. If you use just one cell, it will be total kind of upwinding. There are various schemes available, such as only which use PVD-based schemes, right? And it will take certain number of cells and then bring the information back to this space. And then all mathematics, all splitting on all those things, dissipation, addition will be carried out further using KT and KNP. That is the whole idea of row central form. So typically your solver will basically behave or give a very thin shock structure based on the judicious use of this reconstruction scheme and KT and KNP scheme. So basically there is a two-way coupling for that. Or rather, if I would say KT will behave much more accurately if I use very large number of reconstruction points, right? And if you use very less number of KNP, even if KNP is much more better, if you use only single cell, that it will deteriorate, solution will deteriorate, right? So you have to have the optimum balance between the dissipation that you need to add. And sometimes in the solution, even if you're able to capture very sharp interface, right? Then after that state, let's say the theoretical solution is over here, but your solver will push the solution to very high amplitude and again oscillate back to this particular state. What it will do is, let's say if you have a theoretical solution, right? And if your solver is able to capture this, in reality, no solver will capture. Either it will dissipate, it will capture like this, or it will capture near to the solution, but it will push the amplitude and then it will die down. So this is also not feasible solution because it may lead to instabilities and your code will diverge. So you have to basically take care of, this is the dispersion phenomena. And this is the dissipation phenomenon. You don't want your solver to be very dissipative, otherwise shock structure would be very thick. And you don't want very high dispersion characteristics as well. So these things can be controlled using the reconstruction or interpolation schemes and Krugno-Tadmor or Krugno-Petrov or KNP scheme. So in conduction, you need to use this one plus this one very judiciously. This is the takeaway message from here. So for now, in literature, it has been told Krugno with Van Leer performs very best among all. So this is the default configuration, KNP with Van Leer configuration. And again, SN grad scheme is corrected as I have already told yesterday about the non-orthogonality. So it will take into non-orthogonality as well. Again, if you go to FE solution, this is again typical trivial. This is all the matrix inversion algorithms that has been coded over here. Important entry again, if you go into constant, and there is important property that you need to consider is thermophysical properties. So what we are doing is we are solving for air, right? And for the molecular weight of air is around 28.96. CP of that air is 1004. HF is not taken into account if you use JNF and H constant formulation. And transport, this is in reality for compressible cases, the temperature, the viscosity of the fluid varies like this. Mu s equal to As T to the power 3 by 2 divided by S plus, T plus S, right? So this is what Sutherland formulation is. You might have come across for compressible cases. So for Sutherland formulation, this S is for air, it is 110.4 Kelvin. And A is basically 1.358 into 10 power minus 6. If I'm not wrong, I don't remember that exactly. So thing is like, we are just solving the Euler equation, not the full Navier-Stokes equation. We are just interested in looking the inviscid part. Viscous part has not been taken into account. So viscosity over here has been set to 0. And Prandtl number for calculating, if you are solving energy equation for the heat transfer part of that energy equation or Laplacian part, there is a kappa. Kappa is basically thermal conductivity, and that is related with Prandtl number equal to mu Cp by K. Mu Cp by or kappa. So if you specify Prandtl number, that K will get automatically fixed. So for typically air, Prandtl number varies between 0.72 and 1. 0.72 is very much common literature. So you can set all these input parameters over here. Right. And again, if you go to turbulence properties, you can specify that this simulation is laminar. It doesn't matter because it is already inviscid solution. So this is just a default entry. But if you want to use LES RANs, you can specify all the models over here. You can find that in tutorials of various cases. So today I'm not going to discuss that. Only inviscid cases only I will be telling you. So okay, our system is all set. What we need to do is we need to make a copy. Earlier, let's say by default, our case comes with like this 0.oi original, constant, and system. So first we need to make a copy of 0.org over here and name that as 0. This command will pick up, command will pick up as Control C for this and Control V and rename it as 0. This is what exactly this command is doing. So if you hit enter, it will say 0. This has been copied to 0 folder because we need to set the initial condition. We don't want to contaminate this. As soon as the next step that you need to do is you need to set the initial condition using the set fields that I've already explained you. So for setting that fields, just a sec. I hope till now there is no difficulty in copying that 0.org to 0. So basically now you want to use the set fields command, right? And then hit enter. I'm sorry, there is a bit of issue. Let me figure that out. Okay. There is some mistake in the versions that I have provided. The test file is from ESI version and we are using .com version. So thing is, it will take a little bit of time to fix it. First, oh sorry. Okay, we shall proceed step by step. First, open control dict file, right? And if you see the entry over here, it was again initially adjustable. If you can open it, please let me know what is written over here. Please change the entry right control to adjustable runtime. Type exactly as it is. Then after that, please save this file as resync. Sorry. So go inside system. This is your present working directory. Okay. You do VI's control dict. Open this file. Earlier it was written adjustable. Now you have to write adjustable runtime. For this compatibility, there is some issue. So I have not figured it out. That's why it's creating problem. So write adjustable runtime. If this is over, then please let me know. And please manually delete this particular PDF file. It is creating again problem over here. So the command to do it is rm -rf and type the file name and then hit enter. So it will basically remove everything. Your case is now clean. Please do it up to this step if possible. I'm again reiterating, this has not created problem in the ESI version. It is creating problem in .com version. So I'm basically asking you to customize accordingly to the .com version. We are using OpenFOAM 6. Only thing is you have to remove this particular PDF file. This is also creating